As we've already mentioned, an extremely common use of cookies is as session identifiers, which associate a user with a multi-interaction session with a website. The basic idea is simple. The user first logs into the website, for example using a username and password. On successful login, the server sends back a session cookie with the response. Subsequent requests to the same site will also send along the session cookie. This cookie will either go in an HTTP header or will be explicitly included in a hidden field. At this point, the server now knows who it's talking to. This approach makes the session cookie a prized commodity for attackers. In effect, a session cookie is a capability to access a site with credentials of a particular user. Thus, this capability needs to be protected from theft. Otherwise, an attacker can impersonate a user and perform actions on her behalf. Such actions could result in lost or corrupted data, like your bank account balance. To see how theft could happen, consider where cookies show up in an interaction. First, they are generated and possibly stored at a server. Then, they are transmitted between the server and client and back again. Finally, they are stored at the client for later use. As such, cookies could be stolen by compromising either the server or client and copying them, or if the server's algorithm for generating cookies is known, an adversary could predict what a particular user's cookie is. Cookies could also be copied by sniffing the network to observe them in transit. Or the network could be manipulated into sending the cookies to an adversary directly, using techniques like DNS cache poisoning. Cookie release due to compromise can be prevented by building more resilient clients, servers, and DNS caches. In other words, avoid buffer overruns and the other sorts of errors we've already seen. Now, cookie release due to sniffing can be avoided by using encrypted connections. In particular, sensitive interactions after a login should use secure HTTP, called HTTPS, which encrypts the communications, including the cookies. In fact, by setting the secure attribute of a cookie, you can ensure it will only be sent over HTTPS and never over simply HTTP. This failsafe prevents a coding mistake from inadvertently revealing a session cookie. To avoid allowing the adversary to guess what a cookie will be, applications should generate cookies that are long, so that there are many possibilities for the adversary to try to guess, and random, so that the particular possibility is hard to predict. Note that the same guidelines should hold for generating SIDs in hidden form fields. Now, if, despite these protections, a cookie is stolen, session hijacking can be further defended against by not using only cookies to identify a user session. Instead, you can build your application to require correlating information on the site that identifies a user's current interaction. For example, if the user is currently looking at a web page that shows his bank accounts, but then a request comes in asking for a transfer, the website should be able to tell that the request is not valid. This can be done by storing hidden fields on pages or using the referrer attribute so that impossible requests, even with a proper cookie, are rejected. This same sort of protection is used for CSRF attacks, which we will discuss shortly. There are yet more mitigations against attacks due to stolen cookies. To motivate them, consider a recent Twitter vulnerability. Twitter uses a single cookie called auth token to identify a user. This cookie is computed from the username and password. Now, this approach suffers from two weaknesses. First, the auth token does not change from session to session. Second, it does not become invalid when the user logs out. This means that stealing the cookie gives an attacker indefinite hijacking of a user's account. Now, the defenses we've already discussed can reduce the chances that a cookie is stolen or that it is used inappropriately. But there are two more defenses we can add. First, do not allow session cookies to go on indefinitely. They should have an expiration date. Now, this is like the expiration date on your credit card. It cannot be used after that date. The other defense is to direct a cookie to be deleted from a user's machine and from the server once a session ends. This reduces the time that a cookie is exposed to possible theft due to compromise. Finally, let us consider a non-defense. You might think that you could neuter an attack by tying a session to a particular IP address. That is, a user logs in from one machine, and if requests come from some other machine, they must be bogus and should be rejected. Now, this defense will work most of the time, but there are sufficient problems that it is not usually deployed. In particular, a user's IP address might legitimately change during a session. If using a mobile device, it could legitimately roam, for example, between networks. It could also be forced to renegotiate an address using the DHCP protocol for other reasons. In these cases, a user would suddenly be denied access. In addition to these false positives, relying only on network addresses will miss some attacks too. One example is when a user's machine is behind a network address translator or NAT device. In such cases, hosts beyond the NAT box will view all clients behind the NAT box as having the same address. The NAT box internally translates this address into different local addresses. As such, in a setting like an internet cafe, it's not unlikely that all machines in the cafe will have the same external address. And as such, one machine in the cafe could hijack a session of another machine in the same cafe, for example, by sniffing the network. Once again, the right defense here is to protect the session identifier. Next, we'll look at a related form of attack called cross-site request forgery, or CSRF, that requires similar and complementary defenses.